We're talking about cardiovascular diseases today. So the World Health Organization, cardiovascular diseases are the leading cause of death, not only in the United States, but globally. Cardiovascular diseases represent 32% of all global deaths. That's nuts. Think about that. 32%. That's 1 in 3 people that die of a cardiovascular disease. So here's a chart just to visualize what that looks like. I mean, you can see even cancer, which runs in my family, and I tend to think on the cancer lens. But man, cardiovascular disease coming in at almost double of cancer. 695,000 people in the United States died from heart disease in 2021. That's 1 in every 5 deaths. That's from the CDC. And then 1 person dies every 33 seconds in the United States from cardiovascular disease. But here's the thing. Most cardiovascular diseases can be prevented. So if you find out that you do have some sort of cardiovascular disorder, it's not a death sentence. There are things that can be done about it, which is what we're going to be talking about a bit today, you know, from more the testing side and then what you can do about some of the things that you find. But Dr. Jasbi, you know, being an expert in metabolomics and understanding how these metabolites relate to the body and what that's telling us about the body, and specifically what that's telling us about cardiovascular disease. So today we're going to be disarming the world's #1 killer. We're going to uncover the real villain behind cardiovascular disease. This surprising discovery will radically change your understanding of heart health. So I'm excited to get into it. We'll also learn to recognize the symptoms of a silent heart attack, often mistaken for common ailments. So there are silent heart attacks that people can confuse with other things. So it's good to know what that looks like. And we're going to understand cholesterol's true role in our bodies is crucial. And we'll debunk some of the common myths about cholesterol. You know, everybody talks about cholesterol, but it's already there when the fire is there. It's not necessarily the signs. It can be a good metric, but there's some things that we're going to get into about cholesterol that I think you'll find interesting. Additionally, we'll explore 2 affordable supplements that are surprisingly effective in heart disease prevention. And no, we don't sell those supplements. We're just going to talk about them. And then finally, we'll discuss a groundbreaking heart health test for superior to cholesterol tests for predicting heart attacks, yet rarely used in conventional medicine. And by the way, guys, if you stay to the very end, we're doing something pretty cool. We're doing a giveaway. We're doing a random drawing for somebody to receive an Aristotle test, which is a $750 value. So this includes 9 advanced markers of heart health, not only those, but a ton of other stuff that we'll talk about as well. But here's the thing. You got to be present at the time of the drawing. So we're going to do a random drawing with who's on the webinar right now. And then we're going to select a winner that's going to get this $750 health test. Okay, so get ready for an enlightening journey on heart health. I'm going to hand it over to Dr. Jasbi now.
Thank you so much, Micah, and thank you, everyone, for taking time out of your day to attend this webinar. I'm going to go ahead and share my screen, and we can begin. Micah, can you see my slide set?
Yep, we got it.
Excellent. So, as Micah said, you know, we're going to be discussing cardiovascular disease, and it is the world's #1 killer. So this should be humanity's greatest enemy. With all definitions, I think this is the greatest threat, existential threat, statistically speaking, to humanity, not maybe humanity's future survival, but individual lives. And it's the greatest contributor to morbidity and mortality in us. And we're going to discuss that today. Very briefly, I want to go over and introduce myself and some other members of our science team. Of course, this is just our science team, and Micah is, you know, our beloved leader, our CEO, and we have, you know, various, you know, lab personnel and you know, personal health liaisons that are also a part of our team. But our science team and the core of what we do here is informed by my own work. And the work of my co-founder and chief science officer, who is my former postdoc mentor. And so I specialize in mass spectrometry-based metabolomics, which is good news because that is the majority of what we'll discuss today. My co-founder, Dr. Moore, is a specialist in mass spec and sequencing technologies, as well as bioinformatic analyses. And our advisor, Professor Klein Sitharaman, professor here at ASU's College of Health Solutions with a dual appointment in the School of Molecular Life Sciences. We together specialize in protein-protein interactions, and she's brought a lot of expertise in her in silico simulations and modeling and protein docking experiments, et cetera. And so this is the core of our bioinformatics and our systems biology background. So without further ado, I want to jump into immediately what is cardiovascular disease. So when we say that, it's a very broad term, and in fact, it encompasses any sort of disorder that affects the heart and the blood vessels. And so there are key genetic risks that are associated with the development of cardiovascular disease, or can be considered mitigating or moderating variables. And so those are the sort of polygenic nature of CVD. This is the phenomenon by which a mosaic of genes each contribute a very, very small proportion and account for a very small portion of variance in cardiovascular outcomes. And so realistically, there are hundreds of genes that have in some way been implicated in cardiovascular disease. It is a genetic mosaic, truly. And so this is a very polygenic disorder, not one that is easily traceable to one or a few genes necessarily. When we do talk about things such as familial hypercholesterolemia, which is just a family history of high cholesterol, we do see, for instance, receptors in the LDL receptor gene that is significantly associated with the onset of familial cholesterol. There's also polymorphisms that are related to hypertension. So there are various processes in the body that are, to some extent, genetically regulated, modified, and those are necessarily genes related to salt retention, kidney function, and vascular reactivity, endothelial cell immune functions. And so there are some of these that, of course, together account for hypertension and high blood pressure, which is another risk factor for cardiovascular disease. And there are also cardiac ion channel mutations. So mutations in the actual expressed locally in the cardiomyocyte that in some way creates an aberrant ion channel trafficking mechanism, and therefore leads to poor signal transduction and poor physiological function of the heart muscle itself. And those are tightly related to, of course, heart rhythm disorders, which are genetically intertwined. And then, of course, congenital heart defects. So congenital heart defects I was talking with a gentleman this morning who had a valve deformity, essentially, and how that has impacted his cardiovascular health. And so some of these things are obviously genetic. And when we take into account all of these genetic factors and we look at hundreds of studies encompassing tens of thousands of individuals and systematic reviews and meta-analyses of those results, what we estimate is that for an average individual, genetics accounts for roughly 40% of variance. So 40% of the difference between good and bad health outcomes in the cardiovascular system are related to genetics. So that's good news and bad news, because basically what you're dealt with, the genetic hand you're dealt, basically has 40%, is weighted 40% in the overall equation of how your cardiovascular health will be determined. But the good news is that 60% of it are modifiable. And so cardiovascular disease really is one of those great examples of heterogeneous disorders whose etiology, again, lies in that intersection between genomic expression and environmental reactivity, where you have 40% is influenced by sort of genetic variants and hundreds of them. Sometimes people will talk about their MTHFR gene or their LDLR gene, but those are accounting for fractional amounts of variance when we talk about the total set of a couple hundred genes that are seriously implicated in cardiovascular disease. So 60% of it is totally modifiable. So 60% of the outcomes related to cardiovascular disease can be mitigated and in some ways re-engineered. And that is largely a problem of modern lifestyles. And when we talk about what differentiates here a healthy heart between a diseased heart, I can, just with survey data, honestly, And some self-report biometrics predict, and we've done this, and people have done this in papers. On the left, we see low blood sugar, insulin sensitivity, non-obese, and diet, physical activity, and smoking and stress. So when I ask somebody, this has been shown time and time again in literature, that if you ask someone these 4 questions, what is your fasting blood sugar? What is your insulin sensitivity? This can be either glucose tolerance test or the results of the hemoglobin A1C test. Are you obese or not? And a general assessment of the diet, physical activity levels, smoking, and stress levels can differentiate, without any sort of complicated testing, whether an individual has a healthy heart or a diseased heart. And when we talk, so we don't even really need to really get very much into the weeds here to predict with very high accuracy, and I mean accuracy of 75 to 80% in some studies, where they've asked these individuals these questions, have done the traditional markers of heart health assessment, and have determined whether or not with these 7 questions they can predict if you have a healthy heart or a diseased heart. And what do we say about a diseased heart? Well, there are what we colloquially, I guess, in the science is a shorthand for it. We call these lovingly the 4 metabolic horsemen of cardiovascular disease, of heart disease. And these 4 metabolic horsemen are cholesterol intake, inflammation, endothelial dysfunction, and of course, oxidative stress. And so let's unpack these a little bit. These are the discrete biological processes that happen in metabolic pathways that are arranged as circuits on a board. And these interactions largely determine whether a person has a diseased outcome or a healthy outcome. And so when we talk to LDL, we're talking about cholesterol, bad cholesterol, as it's known, in its processes in plaque formation in the arteries. That plaque formation, that process itself, is known as atherosclerosis. So I want to spend some time to unpack these. And so this bad cholesterol carries cholesterol to various parts of the body. And excess LDL can deposit in the artery walls. And then those deposits, which are of course known as plaques, those are the start of atherosclerosis, and they narrow arteries, they reduce blood flow. And so when LDL gets oxidized, right, it triggers an immune response. The white blood cells and macrophages of the body will then try to digest that oxidized LDL. And then that creates what are known as foam cells, which are, again, a hallmark of atherosclerotic plaque. And then over time, those plaque deposits, they harden or rupture. And then when the rupture happens, that is when we talk about, throwing a clot, which necessarily blocks the blood flow and is the cause of heart attack or stroke. When we talk about chronic inflammation, we discussed this extensively in our inflammatory health webinar. So chronic inflammation is, again, the second horseman of molecular pathogenesis of CVD. This plays a crucial role in initiating and progressing atherosclerosis. So those inflammatory responses that are triggered in the arteries by various factors like high blood pressure or smoking or high cholesterol, that inflammation largely leads to damage in the endothelial lining of those arteries. So it makes them essentially more susceptible to plaque formation because of their inflammation and the damage in that lining. So over time, that inflammation causes plaques to become unstable and ultimately more likely to rupture, which can cause severe cardiovascular events. The third process that is key to monitoring heart health is, of course, impaired endothelial function and its downstream effects. So the endothelium, or that inner lining of the blood vessels, it plays a key role in maintaining vascular health. And so a lot of times we look for endothelial function tests in health sciences. And so the dysfunction necessarily is characterized by that reduction in very essential compound nitric oxide. And it's the key molecule for blood vessel dilation. So this dysfunction can, over time, again, lead to an inability of those arteries to dilate. And if those arteries aren't fully dilated, then it's going to cause hypertension just because of the physical diameter of that lining. And so it really is important because this dysfunction, it facilitates the atherosclerotic progression, and inflammation and plaque really feed on each other in a catch-22 cycle. And then, of course, oxidative stress. We've been talking about it with regard to all of these other horsemen, but it's the damage, right, of free radicals. And we all know that, and we've consumed, I think, enough science as a health conscious group of individuals to know that. But these are highly reactive molecules with unpaired electrons, and they cause damage. They cause oxidative stress in those endothelial cells, necessarily impairing their function. So this leads to a myriad of problems, including, again, inflammation, more plaque formation, and so arterial stiffness eventually. And so this chronic oxidative stress is another process which necessarily has to be mitigated if you are going to halt the progression of cardiovascular disease. And so it's really important, right? Global, we talked about this, right? You said 32%. I think it's 31%, but that's the World Health Organization's latest statistic. You maybe have a more recent statistic, Mike, actually. These slides may be a little bit dated. Chronic impact of, obviously, we know that it's, killing a third is accounting a third for global deaths. Chronic impact, well, it's not just heart disease and heart attack and stroke. Keep in mind that cardiovascular disease includes things such as hypertension, includes things such as endothelial dysfunction disorders or cerebrovascular diseases as well. So it's a very broad umbrella, but there are a few processes that can be targeted with very carefully crafted interventions in order to mitigate that. And then we have these risk factors. So the highest risk factors, we'll get into them more, but we know them. Diet, physical activity, tobacco use, alcohol. We'll go more into detail in the next slide, and we'll order them according to importance as cited in the literature. And of course, there's an economic burden. So just in the US alone, cardiovascular disease accounted for $363 billion in just the 2016-17 fiscal year. And that included healthcare services, medications, and lost productivity.
Well, remember, too, most of it is preventable, which is, and we're going to get to that.
Insane.
But that's the crazy thing, right?
It is our biggest enemy, and we can stomp it out, at least given genetic predispositions. We can lower it by probably 60%. I mean, even being conservative, I would say a 30% reduction is well within our reach tomorrow. And the fact that we aren't is I think, as a health researcher and as other health researchers have opined, is one of the greatest frustrations of doing this science and putting out this work and making this knowledge available. So in the United States, it's the leading cause of death. Every 40 seconds, someone dies. This year alone, 140,000 people will die from it, and 697,000 more will be diagnosed with it. And there's, preventive measures, and there's early detection, which is possible. We're going to discuss the current diagnostic processes and why they're not well suited to routine monitoring, early detection, and proactive efforts. Most diagnostic tests today are reactive tests. They are tests to confirm whether or not you have it. They are not tests to confirm your risk of it one day. They are not tests to assess your increases or decreases in a particular health domain or its underlying molecular constituents over time. They are reactive, and they're often too late. And so we'll talk a little bit about the personal relevance and why it is so important to be mindful of some very easy habits that can mitigate one's risk substantially. So when we talk about risk, and we do meta-analyses, we go in the literature, and we find voluminous review papers that have extensively and systematically included and excluded studies according to certain criteria and garnered the results and performed a systematic analysis of that to synergize and provide us this very detailed synthesis of knowledge. We want to know, what are the top 10 cardiovascular risks? So number one, hypertension, influenced by many things. Lots of it is lifestyle choice. Number two, hyperlipidemia. It's technically high lipids, and high lipids are a better assessment of high cholesterol, but sometimes it's interchanged by physicians, and it shouldn't be. Hypercholesterolemia is high cholesterol, and high lipids is hyperlipidemia. Smoking status, diabetes. So type 2 diabetes is the fourth greatest indicator of increased risk for cardiovascular events. Obesity, as I mentioned earlier, I can ask some very simple questions of anybody and predict with 75 to 80% accuracy the health or disease state of their heart. without, as long as they know these, right? And if they've done their regular routine blood works and they have their blood glucose and hemoglobin A1C, et cetera, we should be able to, with high accuracy, predict the state of the heart. So that's the good news. Physical inactivity is number 6. Physical inactivity in many ways should be its own diagnosis. An unhealthy diet, family history of CVD, age, and a specific gene cluster, the ApoB, PCSK9, and LDLR, the LDL receptor gene. This cluster of genes cumulatively can account for a great proportion of variance. So what you see here are, evidently on the left, modifiable and non-modifiable risk factors. There are some things you cannot change, like your age.
I was just going to mention that. I mean, I'm looking at hypertension and hyperlipidemia, and I'm thinking like, okay, well, those are the things that happen after you've made lifestyle choices.
Yeah, you know, absolutely. They're
which means you can affect the lifestyle choices that lead to those 2 factors 100%. That are going to put you in a risk.
Absolutely. Absolutely. So these are the things that are predicted to, you know, they are predicted to increase risk substantially, ordered in order of importance. And so what we see here is that, again, some are modifiable. You can stop smoking. You can lower your BMI, your obesity, or more importantly, your visceral adiposity. BMI is a crude measure, but you can lower your adiposity in the important regions necessary to lower your risk of cardiovascular disease. But some things you can't change, like your family history of CVD, your age, ApoB, PCSK9, LDLR. These are possibly changeable through some genetic therapies. But how are you going? But just the fact that you've had CVD in your family statistically can be modeled and will increase your risk. So how can you change that? Some things are out of your control. Some things are squarely in your domain. And so what are the signs of dysfunction? When you look at hospital admissions in the literature across continents, across cultures, diets, exercise levels, what are the top 10 signs of dysfunction in people generally? Number 1, of course, is chest pain, angina. These are all what we're talking about in the sense of some of these are together, clustered together, can be the silent heart attack that Micah was mentioning in his introduction. So chest pain is not so silent, but things such as shortness of breath, nausea, or cold sweats, changes in skin color, these are all indicative of sort of, you know, either mini strokes or silent heart attacks that do happen far more frequently than we can even begin to estimate, because we don't have very good technology for continuous monitoring. So those are the signs. And so when we go from order of what's most expressed to least expressed in people, going from what's very general and ubiquitous among people expressing, you know, cardiovascular event, and those a little bit more nuanced, it's chest pain, shortness of breath, heart palpitations, weakness, dizziness, fatigue, swelling or edema, and pain, of course, in arms, shoulders. Sometimes it'll radiate up.
That's not including injuries. That's just pain that comes up without any mechanical
reason. Exactly. Yes. And it's more, and a lot of people describe it as a neurological pain. And sometimes it'll shoot into the lower left jaw area, nausea or indigestion. You know, this is because of certain triggers that are made to the digestive system. Cold sweats, this is another characteristic sign of a silent heart attack. Changes in skin color because, of course, impeded blood flow. And so people may appear pale or discolored as a result of having one of these undetectable cardiovascular events. And so what can you do? Like what is in your wheelhouse? What tools are just basically freely at your disposal? Maybe you need to pick up a script for some other things, but what is predicted to be the best overall, generally speaking? What are the most effective interventions? And so number 1, and you know, they always say if you want to lose weight, you focus on diet, and if you want to increase cardiovascular health, you focus on physical activity. And it's one of those instances where physical activity does account for more variance than the other interventions, and that's pretty much to be expected given the fact that this is a muscle, and its systems and blood vessels surrounding it.
Are
and
these
so,
ranked in order of magnitude of
yeah,
effect
and
that they have?
yes. So one thing I want to mention is that medications are number 9. So you have 8 very good viable options before, more effective options, cheaper, less cumbersome options with relatively no known effect, right? So you can go out and you can exercise, you can modify your diet, your weight management efforts are important here. Again, making sure that you're at least out of obese classification. You have blood pressure control, watching what you eat, increasing hydration, increasing physical activity can again increase blood pressure. Cholesterol management. Cholesterol can be managed through a variety of things. Cholesterol is a poorly misunderstood molecule, in my opinion. But one great way of managing it is niacin therapy. Pharmacological doses of niacin have been shown to have potent lipid-lowering effects, not just on cholesterol, but other lipids that we'll discuss that are very important and often overlooked because of the difficulty in testing them. And so we'll discuss those and their relevance. But cholesterol can be managed before you get on statins. Smoking cessation, obviously, this is an important thing for heart health. Stress. Regular health screenings are one of the best ways to improve cardiac outcomes because they're so prevalent. And oftentimes they go undetected. So increasing the frequency of your screenings and being more hygienic about how often you get screened for cardiovascular health is the number 8 most effective intervention reported in the literature for increasing cardiovascular life in your health span. Number 9 comes in at medications. These are blood thinners, beta blockers, ACE inhibitors. These are statins. And then number 10, so medication only beats out and is more effective than quitting alcohol consumption.
Wait, so quitting, or this is moderate alcohol?
Moderating, right.
Moderating.
I mean, with the goal of quitting, right?
I mean, I don't drink, but I thought this was implying that you should drink some alcohol, but this is saying, hey, reduce it as much as possible.
Reduce it as much as possible. Exactly. Okay. There are actually some benefits to, I guess, to red wine, but it's not the alcohol; it's the phytochemicals in that.
Yeah,
wine.
Which you can get elsewhere.
Right, nitrates are things like that. And so there are some honorable mentions, things that are happening, things that are very exciting in the literature and are quickly growing. And maybe if we did this webinar in the next couple years, we would see some of these on this list as being more proven. But gene therapy, so going to the intracellular site of expression and modifying or repairing mutated genes like the LDLR gene or ApoB to a more, healthful profile. Or stem cell therapy, targeted stem cell therapy to improve the health of cardiomyocytes and to induce their differentiation and progeny in the cardiac tissue. We also have what's next? Nanomedicines. We've seen incredible advancements, some here at ASU, whereby nanobots have been used to deliver targeted therapies instead of inducing very sort of ubiquitous, widespread, interventions and drug treatments. They can deliver specific drugs in specific dosage, very small dosages, only to the cells that need them, using nanobots with certain chemical affinities. And then there's exosome therapy, which is, again, as a delivery mechanism, as a therapeutic vector, has proven to be very important. We do actually recommend certain exosome therapies at Theriome. Some of these other ones so far are either illegal in America, the United States. You can go to Mexico if you want the stem cell therapy, but they're either illegal in the United States or are still very much in the research sphere. But exosome therapy is available and has proven to be useful in some cases. And so this is the landscape of what you can do to improve your cardiovascular health. This is the survey of the literature. And so how do we assess cardiovascular health? So these are the traditional methods of assessing them. And I think everyone has had all of them, if not most of all of them, performed at one point. We have blood pressure. So this is a great and critical indicator of cardiovascular health. It helps measure it helps in assessing the risk, I should say, of heart disease and stroke. So the readings, which are essentially a systolic and diastolic pressure, they provide insights into the heart's workload and the health of the arteries. But it's a very gross, we'll get into that into the next slide. It's a very gross image. Cholesterol. So these measure sort of the lipids in the body. They're not measuring lipids, mind you. They're measuring just the cholesterol molecule. So they have LDL and HDL, which are the bad and good cholesterols respectively. And so high levels of LDL or conversely low levels of HDL can indicate an increased risk of disease. What is an electrocardiogram? So ECGs, these are devices that record the electrical activity of the heart itself. And they're used to identify any sort of irregularities with heart rhythm, but more so structure, right? So they're looking at the structure of the heart itself. And they're essential. They're essential for diagnosing certain conditions like arrhythmias or heart attacks as they happen. And then you have the echocardiogram, and that's an ultrasound. Essentially, it's an ultrasound, and it details the images of all the heart structures and helps to inform probable function, because of course in biology, function follows form. And so it helps in detecting the heart muscle, in detecting any valve problems or cardiac issues, because if the physiology, if the form of the heart is compromised, then necessarily its function will be too. That happens at all scales in biology, at the metabolic level when we're dealing with small chemicals, when at the protein level, or at the organ level, when the form of something is compromised, the function is too. So that's what those tests are looking at. But there's, they're very limited. So these methods, like the blood pressure readings or the cholesterol, they're performed at intervals. There's really no good continuous monitoring tool that I've seen yet. And so those periods can be sort of transient, or maybe they're modeling unexpected changes in cardiovascular health. Most importantly, these are indirect measures. Again, they are looking at electrical activity. They are looking at the high or low levels of one lipid that we, survey, because honestly, most of the things that are traditionally included in conventional tests, many of them are biologically relevant. Most of them weren't the best targets to measure, but with the outdated chemistries of the day, that is what became the gold standard. And now things have changed, obviously, to where the gold standard is what is being done in research spheres. And so these are, they're providing very indirect indications of heart health. So cholesterol levels suggest potential risk, but don't directly measure heart function or blood flow, and they don't speak to the molecular activity. And oftentimes, when you do test them and you see you're high, the pathogenic processes that underlie that increased hyperlipidemia, those processes are already in place, and there are certain networks that are positive feedback loops, so they build on themselves, and unfortunately, that is the case with cardiovascular disease. And so really the tests that we have now, if you're getting them, it is often too late. And they don't speak to the cellular workings of what's happening at that molecular level. And again, non-continuous monitoring. So ideally, in a perfect world, we would get somewhere where these, ECGs or stress tests are essentially an ECG. So I didn't list them as a separate method, but they're often performed in controlled settings. They don't provide continuous monitoring, so it really does limit their ability to detect irregularities. And then it's very difficult to then come back in a lab and do vials of blood draws regularly and do a stress test and do all of these things. And it's a lot of effort to, again, just collect very tangential information that's just tertiary to the problem.
Are those things coming in a little bit late too? Like by the time you have high cholesterol, there are other methodologies that might have found some of the same issues sooner?
Yes, and more important issues, right? So cholesterol is really the molecule that is speaking to, your body's levels of cholesterol. That's it. It doesn't speak how much your body is depositing to your arteries, actually. There are individuals who have very clean arteries and very high cholesterol levels, given things that they intake in their diets that mitigate that. Very clean arteries, very high cholesterol. It is not unheard of whatsoever. And some individuals, can change their diet, and we'll discuss that. But they can change their diet to lower that ultimately. But there is an issue here with cholesterol, is that, again, it is the product of this immune response inside the arterial walls. But that immune response can be detected years before the buildup is postulated to be in the cholesterol in the arteries. And so cholesterol is a very late measure, and it's very asynchronous. So it doesn't really match up with clinical outcomes. When we talk about the synchronicity of a test, we want to have a test that is timely and relevant. And unfortunately, the cholesterol indicator is not. And then they have very limited predictive value. So having an idea of an individual's, ECG and echo, and, let's say we get an LDL and HDL on them, and then we go ahead and do a blood pressure cuff. So we have these variables. They don't actually tell us what to give them. We can recommend certain diets, but what diet? Do you give them a ketogenic diet? Do you give them a diet that is, high in CoQ10? Do you give them a diet that stresses the omega-3s, which are, of course, of great benefit to heart health? What do you give them? And the recommendations, if you've ever been to your doctor, are like, drink less, eat less of this, eat more of that. And it's a very sort of bland recommendation, and has very limited predictive value in diagnosing, really existing heart conditions. There's a reason why 32% of humanity, of humans, are predicted to die of cardiovascular disease. The reason is that these tests don't work. If they worked, we wouldn't be here. Something else would be number one, then we tackle it, right? So testing informs, up to 70% of clinical decision making. So these tests are essential for diagnosing existing heart conditions, but they're far less effective in predicting future cardiovascular events, especially in asymptomatic individuals. That is a very key thing that I want to stress, is that they are essentially not relevant to you if you're asymptomatic. And so what do we need? What do we need in the health testing world? As an individual who specializes in mass spectrometry based metabolomics, so I use a mass spec to analyze metabolites, and I apply bioinformatics to then create tests and workflows that are cheaper, less invasive, more timely. So the turnaround time or time to result is less, because that necessarily shortens the time to diagnosis and the time to treatment. And so
that's just for the listeners. That's science speak for I can find your heart issues.
Thanks, Micah. Well, I think we have a very important panel here, and so and it speaks to the molecular underpinnings of what we monitor. And so we want something that's conveniently able to sample, that somebody doesn't have to come into a controlled laboratory and do a stress test while they're taking their ECG. We want to have direct measures of cellular activity. We don't want to analyze the consequent, which is, in this logical syllogism, cholesterol. We want to analyze its antecedents. We want to shift our approach to cardiovascular health, which we know through those interventions that we've gone through, or any combination thereof, we can reduce the health burden and the individual health outcomes for people who may have CVD progression. And so we want to have direct measures of cellular activity. We don't want to just measure cholesterol when it's already probably in the plaques, in the arteries, forming plaques. We want routine monitoring, and this is what the time to result, eventually cost considerations will go into this, but something that is convenient and can be done routinely to monitor health of the heart, because it is critically missing. And then something that is predictively capable, not just where are you now, but given these experiments or these interventions that I recommend to you, where could you be in 3 months, in 4 months, in 6 months? Or given current trajectories and all else being equal, where will you be in 3 months, 4 months, 6 months? And those kinds of predictive modeling and health engineering projections are needed in a test for the cardiac health. And so that is where, you know, our Aristotle test at Therium comes in. So it is a dry blood spot test that is shipped directly to you. That test then is collected at home. You fill out a little online survey to match with your sample, your barcode, and give us some biopsychosocial factors and metadata that help contextualize your results. Once it is received in lab, we analyze it with GCMS. Then we monitor those 126 sentinel metabolites. And again, it's a very large assay. So this is high throughput, multiplexed analytical chemistry that's taking place here. And we are monitoring levels of these 126, and we're mapping them to known biological pathways in humans. And we're observing for chemical shifts, essentially. And we do that through various domains. We have 12 health domains and 344 different disease signatures we report on. But essentially, the process is the same, is that we are mapping your metabolic data to known metabolic circuitry of humans, and we're observing where aberrations are taking place and matching you to the interventions in the literature that can come in and fix that metabolic circuitry or are predicted to. So what do we monitor that is different than, you know, the status quo? There's a lot. So cardiovascular health, as we said, cardiovascular disease is the disease of the heart and its blood vessels. And so cardiovascular health is the health of the heart and the blood vessels. And our markers here have been mined from the literature to assess the risk of developing those diseases. And as I mentioned, they speak to the underlying cellular processes that underlie cardiovascular disease. We're not looking at the electrophysiology of the heart or the shape of the heart or the which is great when you're diagnosing arrhythmias or potential heart defects, but beside those structural or impulse driven things, you know, we are looking at, which we can also look at actually, but we are looking at the processes such as lipid metabolism, such as inflammation, such as oxidative stress, those processes that at a molecular level are what drive cardiovascular disease and what can be used to assess risk 5 or 10 years ahead of traditional testing. And so we monitor these markers and we score them based on a 1 to 10, again, normalized by some of your self-reported variables. What do we monitor and why? So one thing we monitor is adenosine. It has well-known vasodilatory and cardioprotective effects, especially with regard to immune function in foam cells. So changes here are tightly linked to cardiovascular diseases. And then there's taurine. Taurine, again, is a potent antioxidant molecule. It has very well-documented antihypertensive and anti-atherogenic effects, so preventing high blood pressure and preventing the deposition of plaques in arterial walls. We monitor homocysteine. Homocysteine is a molecule that is, when we talk about pure, sort of chemical association with outcomes, homocysteine has a far stronger and more significant outcome to cardiovascular events than cholesterol. In fact, your homocysteine levels are one of the most predictive biomarkers that you can know about yourself and in your body with respect to your heart health. And so it's not directly measured in our panel, but I'll show you how we assess it using levels of cystathionine and methionine, which are its substrate and product in a molecular network known as the transsulfidration pathway. So we'll talk about that a little bit, but homocysteine, just as an associative biomarker, is tightly linked to risk of future cardiovascular event, and it's not routinely measured. Some of you may have had a homocysteine test. That was probably ordered by an astute physician or healthcare provider that understood the importance of it and its association with heart health, but it's not routinely measured. It's not included in any sort of metabolic panel, and it is a little bit difficult to test. We analyze it, again, using cystathionine and methionine. Palmitic acid, it's a saturated fat. High levels, of course, contribute to heart disease. And these fatty acids are often deposited well before, triglycerides or LDL, HDL molecules. So these depositions of palmitic acid or the lack of, for instance, oleic acid, which is a healthy fat. So if you have lots of oleic acid, your chance of plaque deposition actually goes down. It has to do with the adhesion changing the adhesion of that interior wall, and making it less responsive or less susceptible to plaque deposition. So oleic acid is something you want, right? But if you have, high palmitic acid, high linoleic acid, and alpha linoleic acid, and low oleic acid, this fatty acid profile has been shown in literature to precede the first high cholesterol tests by 7.2 years. This is an interesting finding, and it's been repeated with timelines varying from 3 years to 15 years. But essentially what we're saying is that by analyzing these fatty acids and their relative ratios in blood, we can identify the atherogenic potential of that individual. Because again,
put yes in the chat if you understand that, because that's a big statement.
So what we're doing essentially is saying we're going to not look for the triglycerides and the cholesterols that usually are asynchronous, late predictors of cardiovascular disease. Instead, we're going to look for the smaller fatty acids that predate high lipid scores between 5 or 10 years, roughly, given the study that you're citing. And so we know that these ratios are more important than the ratio of HDL, LDL, but we're not monitoring them. And then finally, niacinamide nicotinic acid. These are critical. So they're both obviously different forms of B3.
Well, real quick while you're taking a drink. So the reason I said that's a big statement is because you said, hey, we're looking at cholesterol and some of these other things. We already know, based on a lot of research, that you can get, an understanding of what's happening in the heart 7.2 years faster than what we currently test with.
Yeah, absolutely. Absolutely. So let me go back. That's the
is that accurate, or is there am I missing the point there?
No, you've got the point. So basically what you're saying is that what I'm saying is that we can look at the fatty acids whose deposition in the blood is, and again, you don't test deposition of cholesterol in the arteries. You test it in the blood and it's inferred in the arteries. Same thing with these fatty acids. We can test their levels in the blood. We have a very good idea of their deposition in the arteries because they're tightly linked, usually. And we can say with, certainty what is, the atherogenic potential. There's always a potential for this individual to deposit plaques, to have that intracellular immune response within the arteries of themselves. And that creates that inflammation, and that creates that plaque deposition. And overall plaque deposition leads to arterial stiffness, and then eventually a clot is thrown, right? So we are analyzing the precursors to the known processes that are often measured. So cholesterol, again, is a very late stage outcome, and oftentimes its presence or its first aberrant testing, can predate the deposition of these smaller fatty acids by 5 or 10 years. And so what are we looking at? What do these tell us? Do they tell us something about the shape of the heart? Do they tell us something about its function? Do they tell us something about, so the cardiovascular health, these are the main metabolites that are used in this domain of the greater 126 we profile. These are the metabolites that are mostly used to model cardiovascular health. There are in fact more. For instance, mitochondrial health, mitochondrial function, specifically 3 processes that are implicated in cardiovascular disease that the mitochondria is responsible for are fusion-fission cycling, genomic stability events of the mitochondria that it regulates, and then of course energy production, so oxidative phosphorylation that we talked about. So of course we weight these cardiovascular metabolites more heavily according to our mining and modeling in the literature. But we still include important biomarkers related to the mitochondria, because of course your mitochondrial health is going to impact your cardiovascular health. We know that this is a very important factor to monitor. The next thing that is tightly linked to that mitochondrial health and often shares a lot of metabolites is apoptotic pathways. Specifically, we're looking for cellular functions and death mechanisms, and we're ascertaining the process, right? So metabolites, right? So when we talk about, like, for instance, this apoptosis, these metabolites that we monitor, they influence apoptosis. They modulate various signaling pathways. For example, when you have altered levels of metabolites like niacinamide or nicotinic acid. These affect the activity of sirtuins, which play a very key role in regulating apoptosis and cell cycle. When you think about the effects on cardiovascular health, this dysregulated apoptotic mechanism, if persistent for some time, it leads to heart disease by either promoting this excessive cell death, which necessarily leads to tissue damage, or it inhibits apoptosis. So it results in abnormal cell proliferation. So proper metabolic balance is really necessary in maintaining apoptosis in those heart cells at a healthy rate. And then there's fibrosis. When we talk about that, when we talk about fibrosis, there's pathways underlying it, such as collagen synthesis and deposition, fibroblast activation. These are what our metabolites are able to speak to. That's something as simple as cholesterol just cannot. And so when we talk about metabolites that affect fibrosis, we're talking about what influences the production of that extracellular matrix proteins. Those extracellular matrix proteins, for instance, amino acids like proline, very, very important that we monitor, are tight regulators of collagen synthesis. And then why is that important in cardiovascular health? So when you have excessive fibrosis in the heart, right, it's very important. So when you have this excessive fibrosis in the heart, we have cardiac tissue is going to suffer. We know that it's going to impair the ability to contract properly. So the physiological pumping of the heart is then compromised. And we know that metabolite regulation plays a very key role in either preventing or promoting this fibrotic process that is a key molecular pathway in cardiovascular disease. And then there's thrombosis, these coagulation processes that metabolites are very astute at monitoring. So we can look at modulating platelet function or coagulation factor. So changes in glucose and lipid metabolism, for instance, that we see in our results, those influence platelet activation and clot formation. And so you can have dysregulated thrombosis that leads to conditions like heart attacks and strokes. And then proper metabolite regulation is, of course, key to preventing that abnormal clot formation. We don't do, echocardiograms. We don't do ECGs. However, we have metabolites that are very sensitive to ion channel trafficking. What do I mean by that? So these are metabolites that can influence the trafficking and function of these ion channels by affecting those membrane lipids. They affect their composition, or they induce some sort of post-translational modification of the channel proteins. And that's really important. It has a huge impact on cardiovascular health, because the proper functioning of those ion channels is essential for maintaining a normal cardiac electrophysiology. And metabolic, or I should say metabolite-related disruptions can lead to arrhythmias and other electrical disturbances of the heart. And now we get to the electrophysiology here too. Again, cardiac electrophysiology, very important, and metabolites are tightly involved in regulating membrane potential. And so making sure that, this altered electrophysiology is properly functioning and identifying any issues that are life-threatening is an aspect that our test is very astute at pointing out. And of course, we're looking at contractility. As I mentioned, we're looking at things such as, enos signaling, calcium cycling. We're not performing a functional test of the muscle, although we are performing a test of those metabolites that are necessarily implicated in the contracting and functioning of that muscle. And then, of course, there's growth factor signaling. That's very important too. So, glucose metabolism can produce intermediates like pyruvate and acetyl-CoA. So those are very important for activating growth factor signaling cascades. And so this regulation of this in the context of heart disease leads to abnormal cell proliferation, which is associated with, again, atherosclerosis and hypertrophic cardiomyopathy. And then there's proper regulation of metabolites that we can engineer and recommend to stave off those effects. And so this is the actual machine in our laboratory. This is our GCMS device instrument that is on the third floor of our research building. And this is what powers it. So this is we're going to open this up in the next few slides and talk about how this is done, but your sample will sit on this carousel here on the arm, and it goes around and it gets injected here, and everything is controlled by this sophisticated, although clunky software that we use that controls every parameter of the mass spec, including, you know, the ramp times of the gas chromatography oven, the injection depths and volumes, transfer line temperatures, all the things that really aren't probably making any sense to you, nor are they necessarily relevant. But that's the actual machine. So we have a helium carrier gas here hooked up to it that actually carries your sample on a cloud of helium gas through the column and then into the mass spec here on the left for chemical analysis and sorting. And so how does this work? What is the process of this? Well, you are the source of metabolites. And after you perform a dry blood spot collection at home, it arrives at our lab, it's marked as received, and then it begins a processing stage where it is essentially homogenized with certain internal standards that then let us quantify what is in your blood, not just say that you have glucose, but say how much of it. And then we undergo derivatization, obviously. So this is a key step in gas chromatography, whereby we derivatize these molecules and we lower their boiling temperatures. So we volatilize them so that when they hit the temperatures of the chromatography column, especially the inlet that is sitting right here. So here is the arm. As soon as this injects, it goes into the inlet. It wants to vaporize that chemical at 290 degrees Celsius. So in order to ensure that everything in that sample is vaporized, we derivatize the chemical structure, changing a little bit and ensuring that it is volatile enough to then fly in the chromatography column. And in the inside is what we're seeing inside that column. What we're seeing is post-column. This is where your sample comes in, again, riding on that carrier gas of helium. It is ionized with an electrical beam shot perpendicularly, an ion beam. And then it's accelerated through various lenses. And for every second that this mass spectrometry run is undergoing its sequence from 0 minutes to 37.5 minutes, we are collecting mass to charges. So for all of this time, right, there's a time dimension and then there's a weight dimension that we use to analyze and quantify these 126 metabolites of the Aristotle test. And so if we take a slice of time out, every slice of time produces what's known as a mass spectra, or a graph of fragments of molecules and their weights and abundances in that sample. And that's how we identify it. So in the context of cardiovascular disease, for instance, you have here, these are the number of the metabolites in our assay. The HMDB ID, the compound name, and then the derivative type, the chemical derivative that we made with our process, and then a retention time. So this is when we expect to see the chromatography peak for this compound, and then we want to see its base peak. We undergo 2 dimensions of separation for everything because, as you can see, for instance, with cystathionine and oleic acid, they both have base peaks of 73. So if you were only going to do mass spectrometry on them, you would be unable to differentiate between the presence of cystathionine or oleic acid. However, by combining that with a time dimension and doing chromatography as a first order separation, we are able to separate them based on time as well. So we know that cystathionine, for instance, comes out at 519 seconds, whereas oleic acid elutes off the column at 555 seconds. And so if we look at the spectra from these 2 time points, we will get 2 base peaks. One at this time is for cystathionine, and the base peak of 73 is for oleic acid. And so that's how we identify and quantify all these metabolites in one run. That's why it's called a high throughput assay. So that is adenosine, as we can see there, its chemical structure and its spectra. Taurine, we have here, again, we've discussed the importance of these metabolites, just to show you. So homocysteine, as I promised, I'd show you how do we calculate it from cystathionine and methionine. So as you can see, methionine is methylated from homocysteine, and then the cystathionine here is produced from digestion of homocysteine. And so by measuring cystathionine and methionine, we are able to infer with very high accuracy the levels of homocysteine in that individual. And we actually do such inferences more often than you would think. And we're able to expand then, therefore, the purview or the coverage of our assay beyond just the 126 metabolites that we monitor, but in certain instances where the metabolic circuitry, we measure adenosine, we measure methionine, and we measure cystathionine, we have certain rate correcting equations that can help us infer, again, with high accuracy, what homocysteine is. And so it is a part of our panel, and we use that level, that inferred level of homocysteine in our modeling with great success. Palmitic acid here, you can see the fatty acid tails on them. Oleic acid, very important. Linoleic and alpha-linolenic acid. And of course, niacinamide and nicotinic acid. So these are the main metabolites. But as I mentioned, we're also looking at metabolites related to collagen synthesis for estimation of fibrotic pathways related to the heart. We're also looking at metabolites of the mitochondria, of the TCA cycle, looking at metabolic perturbations that are affecting the heart, whose signal is coming from the mitochondria. And so our testing is I think a little bit more comprehensive than a bike test and a cholesterol blood draw and blood pressure cuff. And what we do with it is very unique. So we use what's known as digital twinning, and this is a concept that was borrowed from the advanced aeronautical and space industry. Specifically, a group of scientists at NASA realized that there was this overwhelming time and production cost of fabricating an entire, let's say, spacecraft and then testing it in real world conditions and bringing it back down to Earth and re-engineering it and fabricating it again was too time consuming and far too costly. And so what they did was create virtual representations of those parts of a fuselage, for instance, in silico, and then iterate various forces hundreds or thousands of times on that part and re-engineer it again in that digital simulation platform, so that they would cut down on both time to iteration, but also cost, because you only produce something once. And it offers, really, in the last 5 years, it has been drawn into the health sciences. So, engineers sometimes make oftentimes make very, very cool platforms. And so this process, which was inspired in engineering, we brought in. And in the last 5 years or so, growing number of publications in health sciences have focused on the use of digital twins and making them and using them to their full potential. And it really enables doctors or researchers such as myself to visualize those complex physiological processes and identify with a bird's eye view what is going wrong. And so it offers, again, a platform for us to simulate those interventions and testing various health interventions on our customers. And so what we would do is we receive a test from a John, and then we take John and we perform a mathematical abstraction to him, and we abstract him to a metabolic network that is then filled in with his real values, and the color of which will usually denote its significance, and the size of which is how many the abundance of that metabolite, and then we connect them obviously in this metabolic network, and that can be visualized. So when I say digital twin, it's not like a digital you on our screen, but it is an actual network that is produced for you. And then upon that network, we simulate various interventions, everything that can range from medications, but far often than not, those are actually supplementations, dietary changes, exercise changes, changes to your living environment or lifestyle factors that can be modified or identified and mitigated. And so it serves as this predictive tool for us, whereby we take an individual's data and we can tell them where they stand now, but more importantly, we can tell them in 3 or 4 or 6 months where they'll be, all else being equal, or we can use that health gap and help us inform what recommendations we give this individual to improve their health gap. And so we can predict whether they'll be given good compliance to a sound health protocol through time. And so this is the concept of engineering health trajectories, and that is what digital twinning does by actually matching you and personalizing your treatment to your metabolic profile, and more importantly, the predicted response of your metabolic profile we are able to create these very personalized health protocols for our customers. And so that is where, and they'll be very detailed. They're not ambiguous whatsoever. Sometimes I feel like they are too detailed. They're too particular. But after all, these are the results of studies. We take randomized control trials, epidemiological studies, case cohort studies, longitudinal studies, if possible, and we monitor and match you to people who are like you, who have had the similar metabolic profile and have responded in X manner to Y intervention. And if we take Y and we built in 15% randomness on that intervention and simulate it on your digital twin, we observe its response, we can curate a very detailed and predictive health protocol for you that, if followed, will vertically enhance your well-being at that molecular level. And so in addition to providing health scores across key domains, we also do disease enrichment analysis. So this is a service, a database that is compiled and offered as a research tool for researchers and physicians conducting research level testing for their customers, or for their patients, I should say. And so this is a database of 344 disease signatures that have not just been identified, but validated in human blood. There's a necessary difference, because identified just means we have some associations, but validated means that those associations are replicable across different samples and populations and through time. And so these are validated disease signatures, and we take our customer's profile, or the profile of a physician who's performing this test as a sort of very advanced test for an individual with ambiguous disorder, and we will match that customer's metabolic profile to this validated list of 344 disease signatures in the blood. And then we return a list here of which ones they were significantly enriched for. And by significantly, I don't mean like 20%. It's not a percentage base. It's actually considering their type 1 error. So it's a statistical concern. You don't have to worry too much about it. But we only return those metabolites for which we are 95% certain there is not a risk of type 1 error. So we are 95% certain that these are not false positives. And so of those 344, for instance, this individual, returned, I think, a little over 20. And so we see certain conditions related to the cardiovascular system that, of course, are monitored in a similar fashion to our cardiovascular health domain, but are very, very important with regard to heart health, such as early markers of myocardial injury. This individual had 4 of the 14 metabolites matched. And by matched, we mean they have altered in their levels in a way that is characteristic, as reported by this database, that is characteristic of early markers of myocardial injury. Or, for instance, we have heart failures, right? So we have 3 of the 10 metabolites that this individual matched for. We have 10 metabolites in our panel that can speak to heart failure, that are validated biomarkers of heart failure. But of those 10, 3 of them were characteristically enriched in this individual. So in addition to what is given with regard to cardiovascular health and the digital twinning and the recommendations that ensue after we analyze that health domain by itself as a discrete domain, we also have various conditions related to heart health that may manifest on an individual's disease signature report. So I know you're probably at this point wondering how you can get tested for these 9 metabolites, and of course the greater 126 that measure cardiovascular health. So I'm going to hand the microphone back to Micah. He's going to explain how to get that done. And stay tuned, because again, we're going to give away a free Aristotle test, which is usually worth $750, and we're going to give that to one lucky person who's still joined us on live. So Micah, without further ado, please take it away.
Thank you. Appreciate it. Can you take screen share off? I want to talk face to face with the folks. So yeah, and thank you, Paniz. I appreciate you running through all that. Some pretty insightful stuff in terms of heart health, at least it was for me. And yeah, I am going to do the giveaway here in just a second. I do apologize that we've gone a bit over, but we will get to that in just one moment. I just want to share with you guys a little bit about, this test and what it looks like. And I hope, just so you guys understand, like I'm in this business to help people. I'm in this business to try to reduce suffering in the world, you know, with my own journey and those types of things. So I'm coming to you because I love this product and I think it's wonderful, but I hope this was also helpful for you in the sense of like, you learned some stuff that's going to, you know, potentially have an effect on your life. And that was totally free. Right. So, but I think this test is a really big future in the sense that this can potentially become a standard of testing and helping people understand exactly what's happening with their health and what they can do about it. And I find that extremely exciting because, you know, there's a lot of medications, a lot of drugs, a lot of things that we're doing, and not just medications and drugs, but just a lot of things in general that are not good for people's health. So I think this test has the ability of, you know, physicians and so many people have a narrow focus. And I know you guys are a little bit of the on the outside of that, right? Like you're really invested in your health and identifying what's going to be best for you. But, you know, there's so many people that are so narrow focused looking at a very limited scope of health. And I think this test has the opportunity to bring people's head up and see kind of a little bit more of the health landscape as it is and what is objectively going to be helpful to people. So this is going to sound a little bit crazy, but if you went to your doctor with a family history of heart trouble and you were having chest pains or even a heart attack, the only one of these 9 different metabolites or tests that Dr. Jasbi talked about you would be able to get from the average cardiologist is homocysteine, which he did say is important, but we're missing 8 of those other potentials. Like he said, with some good testing, we can get years and years in front of what they are typically doing at an office. And that's only one, you know, the homocysteine is just one. The other 8 tests would be almost impossible to access unless you were a part of a clinical trial or had some regular access to a research facility. So right now, there's only one company offering all 9 of these cutting edge cardiovascular tests to the general public. And that's why I'm a part of Therio, right? I really believe in this company and this project and the future of it. So I know Dr. Jasbi covered it. I'm going to go real quick through this and then we'll do the giveaway. Our Aristotle test doesn't just look at 9 metabolites that measure cardiovascular. So we're not just looking at heart health. We actually look at 126 of these metabolites. Today, we just talked about 9 that are to do with heart health. And we don't just look at heart health. You know, there's aging, nutrition, inflammation, mitochondria, cardiovascular, reproductive, liver, gut, neurocognitive, integumentary, which is like skin, hair, nails, environmental toxicity, and mutational load. So this is the clearest possible picture of your health available anywhere on planet Earth, in my opinion, from everything I've seen. You know, and then it gets into, like you said, the 344 different disease profiles that it can populate. So that goes through several cardiovascular diseases, several types of cancer, many types of common or less common infections, nutritional deficiencies like low B12. I saw we had a question about B3 in there. Even mental health disorders like schizophrenia and autism are actually covered in that 344 different diseases that we've profiled into the test. So what you discover here could help you detect the possibility of the disease before symptoms even start. You know, that's a pretty big deal. Like I think it's going to be, that's why I think it's going to have such a massive ramification is, I mean, one of the things is that we're getting really early detection, but then we're also telling people exactly what to do about it. And it's not biased. We're not selling supplements. We're not selling interventions. We're focused on what is going to get people the best in the quickest way possible. So those personalized protocols. So we do that simulation that goes through 1,300 different tests or interventions that Dr. Jasbi has banked. So that would include exercise routines, vitamins, minerals, herbs, nutritional tweaks, health devices, even lifestyle upgrades. So we simulate those different things thousands of times on your digital twin to find exactly what is going to be the most effective for you. So you'll receive a short list of the most effective combination out of those thousands of possibilities, what is going to be the most effective for you. So that's going to include the specific foods, what you eat, very specific types of exercise, very specific supplements with dosages, how many times a week, at what time of day. And that's all based on the latest scientific research. So again, this is all determined by advanced AI and machine learning. 126 metabolites, thousands of different models that can be created, thousands of different things that can happen. That's why we rope in AI, because they can recognize so many more patterns beyond what is capable of a human brain. We calculated out, it's like somewhere around 90,000 times the amount of data that you would get in a yearly checkup, which obviously it would take years for a human mind to go through that. So that's why we rope in the AI. So in addition to that, we do have consults available if you do take the test with a PhD. We don't just have some tech jump on the call with you guys that got a little bit of training. Like it's very highly educated PhDs, MDs, that kind of thing that'll walk you through the results on things. And that can be really helpful. So as you guys know, this can all be done at home. So we do have a code for today that I'm going to drop into the chat here. I'm going to do that right now. But first, let me cover what it looks like to actually take this test. So you buy the test, we ship it to your house, you do a finger prick, you put about 5 drops of blood onto a piece of paper. That goes back to the laboratory. Within 2 weeks, we deliver your report over email, and then you'll have the opportunity to do a consult with one of the PhDs. And that's how you get access to this test. No doctors, no prescription. You don't have to go to a lab, and all the results don't end up on your health record. So if you have any concern over it, I know athletes are typically a little bit more private about that. But yeah, so if you want to get this test, go to the link that I just dropped in the chat. There's code cardio, gets you 10% off, but that expires on Sunday. So make sure to act fast on that. But without further ado, I'm going to get into the random drawing here. So I'm going to pull it up. Just 1 second. Sorry, guys. And we have Jeff as the winner. Jeff, you do have to send me your email so that I know who you are. Right now, I just know you as Jeff somewhere in the world. So drop me your email. You can do it in the chat here or send it to info@therio.me. Jeff, if you don't claim your test, unfortunately, I do have to give it to somebody else. So just try to do that right away if you can, Jeff. Oh, great. Got your email right there. So we'll be sending you a free Aristotle test.
It's suiting. It's well suited. It goes to Jephocrates. The Aristotle test goes to Jephocrates. I like
Jephocrates. Yeah, it's the Aristotle test, right? Jephocrates, like Socrates, colleague of Aristotle. Or I don't know if that's right, but anyway,
Socrates taught Plato. Plato taught Aristotle. But
yeah,
you're right there. You're right there.
Yeah, close enough.
Yeah.
Yeah, so we're gonna get into Q&A again. Sorry, it's going over. I hope you guys are able to stick around for this Q&A. But let's get into it. Well, here's a good question right off the bat. So do you have a doctor that actually understands test recommendations and implementations, or are you saying you do the test and you can implement yourself?
Both. So we do have MDs that work with us that can provide consultations, et cetera, and help you understand the pragmatic application of those recommended therapies in your protocol. However, no, the heat on our model, essentially the barriers to entry have been very much lowered. And so the recommendations that we give are designed to be self-implementing. You can understand the protocol, the scientific reasoning behind the protocol, and why we want you to retest and when, essentially, is explained in that digital twinning. So even your retest recommendations are informed by the results of the studies from which your simulated effects were mined. And so we do not have really this model that we've envisioned was that we want to provide you the tools to empower your health. And when you look at what can be done for health across the board, most of the time, if you were to rank, top 10 interventions for things, medications are often bottom 5, because there are always a handful of things that can be done yourself, supplementation, dietary changes, very specific dietary changes, and exercise routines, or even cognitive behavioral therapies that can move the needle on protein levels and transcriptomic responses and metabolite levels. These are the tools that have been proven to be most efficacious. And so that's what the protocol is intended to do. And it is meant for the most part to be self-implementable. And we've had instances where, for instance, for an individual who was recommended a chelation therapy, we did work with his physician to show results, display results, and provide justification for why he needed that particular medication at the particular dosage that our digital twinning platform was recommending. And we worked, in a triangle manner with his physician to inform him and get that script. But 99% of the time, these are recommendations that you can implement immediately yourself. The test does not need a physician ordering it, although obviously we do work with physicians and have a special platform for them as well.
Yeah, it's not going to tell you to eat a rare fruit only found on, Mount Fiji or whatever. It's going to be things that are applicable to a lot of people, that are relatively accessible. There are exceptions, obviously. If it's absolutely essential to somebody's health for a particular intervention that maybe isn't so, easy to do, it's going to make that recommendation because it's essential to their health. But most people, we're catching things a little bit earlier and can work with it through diet modifications and lifestyle adjustments and supplementation and all these things that you guys know are to be healthy. So we have a lot of questions today, Paniz. So we're going to have to rattle these out quickly because we have about 10, 15 minutes here and a lot of questions. So what about AFib? What can you do about that? Is it reversible?
So AFib, depending on what is causing it, some of these are genetic predispositions, as I mentioned, related to cardiac ion channels. If it is a genetic sort of defect of how a protein is being synthesized, then we cannot change its expression. What we can do is change what is around that protein and those ion channels specifically. So as I mentioned in an earlier slide, we were discussing ion channel trafficking and all the metabolites that we monitor related to that. And so we can get a very good sense of electrophysiology of the heart. And we have detected things such as potential arrhythmias just based on metabolic signatures. And so we also do include it in our digital twinning. So if it is something that is detected as a significant metabolic signature that warrants addressing, the algorithm will necessarily pick that up and formulate a protocol to address it under the cardiovascular health domain.
Great. Deborah commented, I'm 59 years old with APOB 141, CT calcium score of 0, and LDL of 208. HDL of 92. Very concerned, and my inflammatory markers are increasing. Oddly, I have not felt bad, but I do have heart palpitations. I'm going to skip down a little bit. I'm pretty healthy. Do you check mineral levels? And is it a gut inflammatory issue potentially?
Right. So you mentioned mineral levels. I don't know if you're predisposed to ApoB, PCSK9, and LDLR, and please don't think that because I discussed them, they are super prevalent and they are affecting you, and your health is compromised. That's not absolutely it. If you haven't felt if you've been asymptomatic, that's wonderful, fantastic. It doesn't mean that you are free of cardiovascular disease. Absolutely not. In fact, the major issue that we have with current health testing efforts in the cardiovascular health is that they're not predictive or applicable to asymptomatic individuals. And so I don't know if it's related to your predisposition. When you talk about mineral levels, minerals are too small. We don't actually detect minerals, although we detect things that are related and built on minerals and act upon minerals. So just like we showed with homocysteine methionine, we do infer to certain mineral strengths. So for instance, if you have poor ATP, chances are your magnesium is low. And we don't directly monitor magnesium, although magnesium is one of our most recommended supplements. And we can give that in various forms. We can tell you to, depending on the results of your digital twinning, in which there are PK and PD simulations, pharmacokinetic and dynamic simulations that tell us what source of food you're best to take. So we can tell you to take your magnesium from natural sources, take it as magnesium citrate or glycinate, whatever the case is, we can actually match you with a specific formulation. But I don't know if it's the minerals. The only way to know is to get tested. It may be gut inflammatory issues. And we do have a very sensitive domain that looks at gut health. And so we can render a score on 1 to 10 on gut health and then simulate and postulate what the issues are and infer even the first few dominant taxa of your gut given the metabolic expression. So when you talk about ApoB, it's a protein that's involved in lipid metabolism. It's a component of LDL, and it's often associated with that, an increased risk of cardiovascular disease. However, the interpretation of an ApoB level should really be done in the backdrop of your lipid profile components and cardiovascular risk factors. So when you do take our test, hopefully you will take it and you will fill out a survey in which we ask for any known genetic mutations. And so our model is able to stratify individuals with or without certain mutations like ApoB when assessing things that are relevant, such as cardiovascular health or Alzheimer's disease. When we talk about your CT calcium score of 0. So it actually, that score suggests no detectable coronary calcification, which is, a really positive indicator for you in terms of cardiovascular risk. However, a score of 0 doesn't necessarily eliminate the risk of heart disease either. And then you mentioned your LDL level is high here. So that typically raises some concerns. But again, your HDL is also high, which is usually considered protective. So the ratio of them, along with other factors like ApoB, really need to be considered when assessing your cardiovascular risk. And then inflammatory markers, obviously, these are increasing and they could be significant. It's a known risk factor, obviously, in inflammatory pathways for CVD. But the specific markers and their levels are important to consider. And inflammation and mitochondrial health are the two other domains that most greatly influence our calculation of cardiovascular disease risk and your relative health in that domain. So inflammatory markers are also considered as part of our testing. And then, those heart palpitations and your fasting insulin and HbA1c, these are within normal ranges. These are all very much encouraging. So you can do a genetic test for your ApoB, PCSK. You can look at mineral levels, and you can do separate testing to look at gut inflammatory issues. But with our test, it's a very convenient direct-to-consumer test that analyzes more data points than any other test of its kind on the market. And not just analyzes more data, because oftentimes analyzing more data never translates into delivering better insights. And so just as important as the vastness of your data collection apparatus, you need to consider the sophistication and inferential potential of the algorithms that then plug into that data. And as Micah mentioned, we are very much in the bioinformatics business. And so what do I mean by that is that what separates our levels of testing are the levels of analysis that we return to you. We always collect the same amount of data, but and this model is complete in the biotech industry. But what we're essentially doing is installing a vast network of over 15,000 models that inform each other. And you heard that correctly. Every report, there is a need to generate more than 15,000 models. In fact, it's so cumbersome that each report takes about 16 minutes, and we have to connect to supernode clusters in order to generate and chug through that data. It can't be done on a regular laptop. And so we are, undertaking a very analytically cumbersome challenge. But I think, to your question, yes, it could be all of these things, or it could be none of them. But I think the cardiovascular health metabolites that we assess in the Aristotle test are a very good indicator. And if we do see those issues, we are very astute at picking them out and addressing them with our digital twin protocols.
I see a couple questions about the test, and I just want to clarify something. So, for example, Janice asked, how is this different from Theriom's metabolomic testing? Well, today we're just talking about cardiovascular. So we have the test, right? It's $650. It gets you everything that we've talked about. Today we're focusing on cardiovascular because that's one part of the test. So this is not different from the metabolomic testing. This is the metabolomic testing. It's just we take these webinars as an opportunity to provide some education on different topics because there's a lot that goes into this. we're going to have hours and hours and hours of webinars and videos and articles and reading just to educate about what this test is doing and then that kind of thing. So I hope that provides some clarification. The $650 is going to get you everything you need, and it covers cardiovascular as well as, things we've talked about previously, like the neurocognitive index, the liver index, and all those various things. It looks like Deborah asked a question. Once you identify what is going on with the test, how do you implement a successful program to mitigate and reverse? I think that was before the digital twinning talk. So,
Exactly.
like Dr. Jasbi said, they take your data, they run thousands of simulations to find what is going to be the most effective for you, what's going to get you the best, the quickest, and that is where the protocol comes from. And that's in that $650 test. Tom asked a question: can homocysteine levels change from day to day? And if so, is it difficult to follow these levels during therapies? In other words, my infusion system requires 10 to 20 doses. So how often should I test the patient?
Yeah, that's a great question. So homocysteine levels absolutely can and fluctuate due to various factors such as diet or lifestyle or metabolic state. However, these changes are typically not drastic from day to day unless there's a significant change in diet, particularly intake of folate, vitamin B6, vitamin B12, or lifestyle. So for therapeutic purposes, especially when monitoring the effectiveness of a treatment regimen, it's crucial to understand the best practices for testing homocysteine levels. And so there are data that on the subject, on the patient, you should collect, and that would help contextualize their homocysteine levels throughout this protocol that you want to implement. But you should collect some data on dietary intake. Foods, again, rich in folate, B6, and B12 can lower homocysteine levels. So conversely, a diet that's deficient in those nutrients can increase levels. And so having a data measure on that is important. Lifestyle factors, knowing if the patient is smoking or consumes alcohol, the frequency or the lack of physical activity, all can elevate homocysteine levels. So having some awareness of that, I think, is important before you begin testing them. Genetic factors, of course, certain genetic mutations can affect homocysteine metabolism, MTHFR being one of them. And then health conditions, kidney disease, hypothyroidism. What else is implicated? These all influence homocysteine levels. So monitoring that during therapy, it has to have a sort of nuanced approach. Should be an initial testing period where a baseline level needs to be established before starting a therapy. And these can be, an average of a few days or an intraday average, et cetera. And then the frequency of testing, I guess, depends on the specific therapy and the individual's response. But in a scenario where a patient is receiving 10 to 20 doses of an infusion system, I would say it's advisable to retest homocysteine levels first after a few doses, just to assess early response to the therapy, and then midway through the therapy to, again, monitor any progress or adjust the therapy if needed. And then post-therapy, so to sort of do this evaluation of the overall effectiveness of that treatment. And when you do it, I would say it's very important, given what I know of homocysteine metabolism, to maintain some consistency in those testing conditions. So important to maintain conditions like time of day the sample was collected or fasting state to have a more accurate comparison. And then if you are, yourself the healthcare provider, obviously that decision is up to you. But be aware of any changes, like I said, in diet and lifestyle, because that can confound any effects of the treatment that you may see, and either increase or exacerbate them. So they can vary, but a structured approach to testing is possible. And when that is implemented, you should be able to effectively monitor those levels during therapy. So the frequency is usually, obviously tailored to the person's response, and if you're doing this, then be qualified, obviously. But that is how you should structure, is to control, to collect data on confounding variables, and to make sure that you're getting a baseline and some recurrent monitoring.
Very cool. Very good. Well, I want to thank everybody for joining today. Again, the cardio discount ends on Sunday. So if you want to get this test that includes everything that we talked about, including the cardio, plus the liver, the brain, all that good stuff, click the link in the chat right there, or you can go to www.therio.me. That's a way to do it as well. By the way, please feel free to contact us. Be happy to talk with you more, anything that we can do to help, even if it's just education. We have more materials, more things that we can offer. So again, code cardio gets you 10% off, expires on Sunday. So click that link to buy it. And again, thank you. I appreciate everybody's time, and we're going to wrap this up and hope you have a fantastic Tuesday.
Thanks, everyone. Talk soon.
Bye.
Bye-bye.